Thanks very much for the invitation to join in. I am absolutely passionate about this question that the world, especially the United States, really needs people who can manage and make decisions with very large amounts of data, and it's our responsibility to build those people. And the way we build them is to make sure we train them up with the skills and to respect the skills of other people who've got complementary abilities. And one of the reasons, it's going to come up later on in this talk, I spent 10 years at Google where I was responsible for the machine learning systems which drive Google advertising. So very large models and some very small models where we had to do very careful analysis. And in that role, I really had an opportunity to learn why I cannot say, I just need computer scientists, or I just need statisticians, or I just need electrical engineers, or I just need product managers and product designers. You're always building teams, and you don't try to hire folks who can do everything. So one of the nicest things for me, and the reason that I decided to come back from industry, was Carnegie Mellon is a place where if you love data, it's a pretty good life, because we happen not to have awful turf wars. And I was actually going to talk a little bit as to why I think we lucked out in this way, because I think there are some lessons here which can help as we decide as a community how statistics and computer science work together in the future. So we have a really nice statistics department. Lots of friends. I hope you recognize some of these faces. There's Larry Wasserman looking like a criminal. Many people. We have about 45 wonderful statistics faculty, spanning the bridge from folks who purely love the math behind it to many folks who are involved in large science and engineering problems. And then we have folks in a machine learning department, including Tom Mitchell, who was a big figure in machine learning, frankly, before he'd ever heard of statistics. And he embraced it when he basically, because I was a junior faculty at the time, he came to the realization that machine learning had erroneously just tried to reinvent a bunch of stuff which was already working pretty well. And instead of putting up the castle walls, he immediately reached out to the statistics department, and over a period of about 8 years in the late 90s and early 2000s, insisted that the statisticians and the computer scientists really get together and don't worry about definitions or what our purpose in life is, but what are the next big problems that society has that we can use for doing this stuff. So we have many wonderful folks on both sides, and my job as an administrator, of course, is to make sure these people are successful and to remove barriers for making them successful. That's what I have to do. And one of the things that really helps me is this. You move so much faster when you're not having these raison d'etre type discussions or anxieties all the time. So to some extent we're lucky that this happens, but on the next few slides I'm going to show you what I believe and what we have a consensus among our faculties is the reason that this is working. And just to mention, as it happens, because this is going to be relevant in Carnegie Mellon, the statistics department is part of the College of Humanities, Dietrich College of Humanities, which is separate from computer science, which is its own college. 7 departments, including core computer science, robotics, machine learning, computational biology, where, by the way, I've got a whole bunch of departments which have a lot of similarities to each other, who could unproductively spend all their time wondering about who's responsible for what, but usually manage to get over that. So let's talk about how we can get this to work. And frankly, one of our secret weapons at Carnegie Mellon is that some of the other major universities, which we are traditionally regarded as being in competition with, have not produced this kind of love affair between disciplines. And that is one of our advantages going over the next 10 or 20 years, which I think is going to help us prosper. the secret truth is I'd actually like it if other universities had this harmony as well. Here's another example of what happens at CMU. These are a mixture of statistics PhD students and machine learning undergraduate students. When the G20 summit came to Pittsburgh, and everyone else was protesting things like globalization and immigration, so these guys marched with them and confused the whole city. I really like Bayesians against discrimination. That's an absolutely perfect one. And then reveal parallels. Anyway, so it's a mixture, and these are young, really smart folks who actually don't know everything that each other's doing, but they just learn to live with each other. If you just search for a CMU statistics protest. Okay. All right. So again, what I want to communicate is things which I think work, so that in case they can help in this discussion, and I and folks like Chris Genovese, Larry Wasserman, Steve Feinberg at Carnegie Mellon, we'd all be delighted to follow up if folks want sort of tips or dare I say it, marriage counseling, this kind of thing. We're like the insufferable couple who keep saying how they love each other for the last 40 years. Okay, so why does it work? Okay, number one, I don't think it's because we're nice people. And that the kind of conflict that you've been talking about and worrying about here, it happens elsewhere. And there was another instance of this recently on CMU's campus where the university did a much worse job. And this is in the area of cybersecurity, very important thing for the world. And that, if you like, is actually kind of the domain of computer scientists, networking expertise, electrical engineering folks, and these straddle usually computer science departments and engineering departments. And we've got peace now, but we CMU squandered probably 10 years, and we lost some really good faculty because we had different camps of cybersecurity. Literally, folks would visit campus, and one camp would grab them and say, talk to us, don't talk to those jerks, and vice versa. And there were the kind of the theoretical computer scientists talking about security. Sure, they can write nice theorems, but it's not going to save the world. And then the computer scientists say, there's engineers, they're just a bunch of hackers, they're just coming up with ad hoc solutions. Neither of those were true. So we blew it. We probably be way, way, way ahead of any other institution because of the talent of the faculty that we've had in these two areas, but we lost our way. And about 2 years ago, we rebooted it with a new provost who came in and kicked us all around and said, get your act together. And we finally got past that. But that's why I don't think that we can credit CMU as being just full of a happy faculty. It worked here for some other reason. So another thing which sometimes comes up, and those of us at the dean's level or other people who do administration rather than real work are very familiar with all these questions of, should we be using a resource, an RCM model, should we be paying each other for butts in seats and those kinds of things. We do that really badly at Carnegie Mellon right now. We've got economics which really would incentivize people to be selfish and do these stupid things like the computer science department running its own statistics course, or even the statistics department running its own computer science course. The economic incentives are there, but we've avoided doing it. Anyway, so it wasn't because we had an economic system which prevented us from being selfish. And this is not really fair. I don't think there's any trouble in creating centers. Carnegie Mellon happens to have a center, an excess of centers. I think we probably have more centers than faculty, but I haven't actually counted. But one thing that you could imagine we could have done, this is exactly what went wrong for us with cybersecurity, by the way, is to decree at some point we're going to have a new institute for, depending on which year, e-science, grid science, data science, big data, Internet of Big Data Things, something like that, and tried to use that to get the campus working together. Now, we did consider that, and some of the higher academic administrators wanted to do it because they know that data science is the cool thing, and they know that governments are looking to fund things with that in them. But the problem is, we thought about it, we looked around campus. About 75% of all the faculty on campus are doing data science if you use one of these white papers about it. And if we set up some institute and had to go to different faculty and say, you're in, you're out, you're in, you're out, it would be a disaster because we just want people to be working together and not worrying about the labels. So we made the conscious decision not to do this. We're certainly going to do huge amounts of work with data, and many of our faculty are motivated. That's what their whole careers are about. But we're not going to, we made the explicit decision not to do it by the formation of another center or another institute. So, here's the trick. Here's the thing which worked. I'm one example of this general principle. It is very much as the speaker mentioned there, we just try to get the faculty, and we've had this culture which comes from the founders of the various colleges at CMU from decades ago, that you're not here to do stuff on behalf of your department or your college. You're trying to build something for the rest of the world. And so you've got to pick something big, and it's not just statistics for its own sake or computer science for its own sake. You take some of the big challenges of the world and you get the students, those young idealistic crazy people, excited about those, and then the faculty help them. And that's when, if you've got a discipline which is worth anything, you find that your discipline can help in solving the problem. So we have many, many examples of this kind of thing. Here's just for as you all know, there's really interesting problems in analyzing very large amounts of data from telescopes. We had about 4 physics professors. There are about 3 of us in computer science, and then there was Larry and Chris in statistics. One of the physics professors got us really excited that dark matter at the time shouldn't be there, and we had to find out why it was. So we all worked together on it, and Chris and Larry really had to push hard on refinements to Benjamin and Hochberg, because we were doing stuff on about 1 billion observations of galaxies. I had to work really hard with them on their crazy ass non-linear scoring functions. Some algorithm designers hate it when it's non-linear, to make the computation practical for looking at all of these. Of course, the physicists were there inspiring us, and as we were doing it, that's when I really learned statistics. That's when the physicists learned statistics, and that's when Chris, at least, I wouldn't say this for Larry, actually learned how to respect proper algorithms. We had so much fun doing it, and it was really great. And we weren't thinking about centers or labels or definitions while we were doing it. Same thing here. A bunch of us, including people from the University of Pittsburgh, got really interested in the potential, given the availability of data. This was in about 2005, when we had access to all the pharmaceutical sales in the country and all the health records for emergency admissions into hospitals in the country and a bunch of other things. We all believed that we could do something very useful in predicting new kinds of outbreaks and detecting sort of geographically dispersed disease onsets. And there's a fantastic sub-discipline called spatial scan statistics in the statistical community, and a bunch of folks pushed together on that. And in the end, many of the systems that they built have been productionized, and even now the professors hear stories of how they save lives in various parts of the world by identifying outbreaks early. And so that's the big win, and that's usually the science paper, but then subsidiary to that in the conferences are papers about the algorithms to make it scale, or the new models to deal with, as you know in scan statistics, the ridiculous amount of oversampling that happens. And then just to build self-driving vehicles, which Carnegie Mellon did in the late 90s and really brought to prominence in the 2000s, there are a bunch of statistics faculty who actually worked on this. Everyone in our robotics institute, the grad students doing their PhDs there, they all learn detailed probability and statistics before they start building the sensors or the actuators on these vehicles. So having folks working together on products, on projects, we see as the absolute key to getting this sort of piece. I'm going to move over to the education side of this, because research can bond folks together, but education is really important. So one of our absolute requirements in all our machine learning related curriculum and our computational data science curriculum is that you begin with probability and statistics. If you're hiring someone to help you out in some of the analytical end of what you're doing, we don't really care whether you know about decision trees or association rules or these sort of computing-like algorithms. We really, really care whether you actually understand what sampling means, the various non-parametric tests and the parametric tests from the past, and that you're able to construct graphical models is what we usually use of how all the signals in a system join together. This thing, very much like on Game of Thrones, what you do to make sure two great houses don't fight each other is you have hostage swaps. So some of our junior faculty, like Ryan Tishirani, comes and actually co-teaches the machine learning course, and some of our faculty, like Arti Singh, goes and teaches some of the introductory statistics courses. And what's most important there is that the students learn to respect each other and get to know each other. Now, here's something which we've used, which I think has helped us a lot. We always talk about data science. We don't say data science, we say the data science stack. And many of you have heard of the computer networking stack, where some people on that stack work on the atoms level of making very fast transducers. Some work a little higher up on routing and DHCP. Some work higher than that on some of the network protocols, failure omission. Some of them work on browsers and protocols for high-level applications. And they all need each other and they all support each other. So as we're teaching data science, we really value people who say at one level they're going to do some work, become an expert at something, and then really take advantage of the help from the people below them. They know enough about it that they can be useful, and they support the people above them, and this is what gives you a lot of meaning. If you're writing a really clever new GPU system to be able to do dot products of billion length vectors faster than anyone else before, the only joy you're really getting from that is knowing that it's helping some of the modeling people, which in the end helps some of the people who are building decision support systems out of what's going on. So the culture and the emphasis is that there exists something, this is probably the most important slide in this talk, there exists something called the data science stack, a whole bunch of capabilities, and you as a person can choose if you're going to have expertise in one or two areas of that, or if you want to be a kind of generalist and know a little bit about all of them, and you're depending on and you're having respect for the people above and below you in the stack. You're not saying my bit of the stack is the only one that matters. And working that way, it makes it much easier for our students and our junior faculty to understand each other and learn to appreciate each other. So if a computer science algorithms faculty starts to work with a statistician, it's not the case that the computer science algorithms faculty should forget what they know about algorithms and try to be a statistician. They should work out how they can help each other. So this, I think, is extremely important, and I much prefer to talk about the data science stack rather than spend a lot of unproductive time worrying about what exactly is data science. Because with the data science stack, I can just say there's a set of capabilities that you can train people up on and you can utilize when you need them. Here's one example of why we need respect and folks working together. This was a very fun project. We did it just before I headed out to Google. And there's a hand-star telescope. It's something which takes about 1,000 plates a night looking at the sky. And you can, as you see, these ones look very obvious, but sometimes you do get to see things which are probably objects, and you have to do statistical testing over the plates, taking into account a lot of dangerous possibilities to find out which one of these are actually objects. What you're trying to do, at least what we're trying to do in this, is infer if there are near-Earth orbiting objects out there which are very, very faint. So typical physics projects which, after they've discretized the data, they've taken out these very large spots, and they get a few of the moving spots, but sometimes moving spots are not very high signal. This one is relatively high signal, some of them are much less. Now, if they were, in general, moving in a way where you could see them close to each other on the sky each night, you could quite efficiently detect them. The truth is, though, that the telescope can't afford to scan the sky each night. It's being used for other science, and so you actually need to get evidence over several months from about 5 or 6 potential sightings of the same thing. If you're going to write out, first, you've got to be very smart then, as you can imagine, about the modeling of the observation noise and taking into account the observation bias when you're hypothesizing that you've seen a track. So that's one big piece of work. Another big piece of work is the right way to do this thing. If you're looking for the sets of 6 observations which might be in a track, is to write 6 nested for loops in R. So for all objects, 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 do a statistical test whether this set of 6 objects forms a track. And of course, in this case, this is one of those cases where it's not crappy fake quantitative data. This is moderately big. It's billions. Industry is usually doing trillions, but that's enough that you know that you can't do 6 nested for loops. So it is a very real and really interesting algorithmic question. How can you have the computer quickly concentrate only on potentially useful tracks? And there's some really beautiful tricks using spatial trees, which incidentally Bill Cleveland was one of the pioneers of in computer science, which allow us to do this. And now this system is running, has discovered a few hundred dwarf planets and some near-Earth object planets, and it would have been dead in the water if we'd just done the algorithm, because the amount of danger you get from using such noisy signals with such massive computation is too great. And it would be dead in the water if we'd just done the statistics. If we'd just done the statistics side, we'd be running this on only very bright objects. So it's a nice story. Google Pittsburgh, which started in 2006, currently has 800 people in it, and they're all devoted to modeling and predicting the behavior of users, specifically the question of, given the user made this query, and assuming we're going to lay out this page of results for them, what is the probability that they will click something on the page versus using their back button, and what is the distribution of the likelihood of what they're going to click? So it's a very interesting prediction task. It is much more than a simple 0-1 loss prediction problem, because there's huge interactions between whether I show a big bright image here, especially if it's Britney Spears, it's going to massively affect whether someone clicks something down there. So it's a fantastic problem, and it's just wonderful. First time in my life I've needed to do dot products of vectors of length 1 trillion. Right? When you've got so much data, and this is scientifically interesting, you can actually build these ridiculous models with billions of parameters in them. There can be a parameter for the typical behavior of someone in Belgium who's been looking for housewares on a rainy day after there's been a major news story about a rock band. One of your parameters can be that. So all kinds of engineering tasks in doing this, and so that's a lot of fun. we had to hire really good people to do this, and we hired them from around the world, and we found the very best people. And we rarely said, I mean, we're delighted if there was someone who could do everything, but what we respected in the hiring was people who were experts at one area, but were curious and loved hanging out with the people in the other areas. So we had some, we did a raid on, I shouldn't say that, especially on camera. Okay. After some recruiting activity, we had a bunch of very, very strong folks who are really good at networking and file systems. They were the people who built a brand new generation of machine learning systems. And they did it by painstakingly understanding the statistics and then the linear algebra which supported the statistics, and then thinking about how you can have signals between multiple machines and data centers which might not even be in the same, data clusters which might not be in the same data center, being able to update themselves in a way that was stable. So it was a beautiful story, and we only got that by finding folks who had complementary skills at different levels of the data science stack. And I would be horrified if instead of that, universities were producing for us folks with a little bit of skill everywhere. That would be much less useful. The whole point of university systems is so that people can become world class in some areas. And while they do it, they have to have respect for the other areas. Okay, fine. I won't go into this. There's a very interesting story of what's happening now in artificial intelligence. And artificial intelligence is the thing which is built on top of the data science stack. As we can model the world and understand it, that's when we start to bring in the successors of Apple's Siri, guiding us in our lives, and full autonomous systems which will make a decision in a quarter of a second if our car is about to crash dangerously as to how to best save as many lives as possible. So although these areas are going to grow, every one of these areas needs each other and is going to grow. I think it's going to be even more inspiring because of the big autonomous and cognitive systems we're building on top. Oh, and I mentioned Carnegie Mellon's evil plan. So here's our evil master plan. And it's really good, and I hope you'll approve. So we have just hired a new dean of the College of Natural Sciences at Carnegie Mellon. This is the college with physics, chemistry, biology, and actually mathematics. So that's good. It's still an evil plan to make sure that we are continue to be leaders, at least we hope to be, in the world of data. And the reason is, statistics is not in the College of Science, but she's a statistician. She's awesome. And so we have College of Humanities with well-adjusted faculty that include a world-class statistics department that love working with the computer scientists, where we have very much a culture that you cannot be a meaningful computer scientist without understanding probability and statistics. And now the master piece in this plan is that in our science school, where we're doing all the big physics which needs this stuff, it is being controlled by a statistician mastermind. So the final comment on the slide, she's not actually evil. So that's it. Thank you.
We have about 5 minutes before we go to the next speaker.
Thank you.
I have a question. I think that I love this. I love the idea of collaborations across different departments. But I have a very academic question.
Yeah.
Because I'm in a situation where there's still people making decisions about promotion and tenure for my faculty who are very much, you have to be PI, you have to be first author. How did you change that culture so that a very collaborative environment could be valued and that faculty could be successful?
That's interesting, actually, and I think it is a very important thing. So my predecessor as dean famously got extremely angry at one university promotions meeting because people were actually starting to count papers and citations without realizing that this particular person had built something which was fielded, saving about 300 lives a year, and it was very technologically advanced and interesting. And that was the point where we made it really clear we're making tenure decisions based on impact. And that's not the only, you don't have to have done impact. Obviously, in business schools and so forth, they're not going to build systems. But among the values among CMU deans and the provost are that we really value, and we say it all the time to the faculty, don't worry about publishing, we need you to have impact. And we do then, I've tenured people who've only got 2 journal publications a year for the last few years, but they've had huge impact. And so that matters. So, and then we would never look at like who was officially the PI on something. We do when we're doing earlier career management for the junior faculty, so reappointment to assistant and then assistant to associate, which for us is not tenure. At both of those stages, we mentor faculty who seem to be trying to be a lone hero, because in the complex world that we live in, very few fields where you can actually get anything done if you don't collaborate. So we coach for that. We the leaders talk about it all the time, but it required my predecessor, who was pretty heroic about this, to really go nuts at one point to sort of spread this culture.
Dick Sager also set a culture way from the beginning.
Yeah. I don't want to say that it was all just that. It was right from people who founded Carnegie Mellon, then Herb Simon and Alan Buell, who did the peaceful move of computer science out of mathematics. We've had that kind of set of values, and that's helped us a lot. And so the flip answer is make sure you're at a university which has these values, and then but the more practical answer.
I am now.
Okay. the practical answer, I think, is it is something which, as people are choosing academic leaders, looking for the folks who've got this track record that they themselves, earlier on in their career, decided that they were actually going to do something based on impact rather than just academic points, and that they seemed to like to find people with complementary skills to themselves. Yes?
Yesterday, there was a lot of discussion about having a broad and deep training for every student in that context, and in the context of what you said. What will you recommend? T model, broad, deep.
If I think what you're saying, if what you're saying is what I think you're saying, I'm totally on the same page. So I'm very happy for even an undergraduate to get a lot of training in one of these areas, assuming that they're doing minors, they're doing courses elsewhere. But just to be an expert in any of these areas, you can't just have a delta function here. You have to know something about the areas above and below you. So there is a minimum threshold. Now, one thing we haven't sorted out yet at Carnegie Mellon, though, is I, as dean, and about 50% of my faculty believe that some of what we used to think as basic computer science could be replaced by formal grounding in more advanced probability and statistics. Of course, we have probability and statistics requirement in undergraduate curricula, and it is much more than the stereotype of boring statistics like the AP statistics. It's interesting stuff, and it means that people can come out talking about and understanding conditional distributions, marginalization, and all those issues around that. But I would like us to go further, and one of the things that's happened at CMU and many other universities is now about 2/3 of the undergraduate population across the whole campus takes the computer science 101 courses. Our computer science students all take the stats 101 courses, but then we don't insist that they're taking stats 201, and in fact for many of us it's actually the probability side, which is really important, especially as you're building the AI systems on top of it. So I'd like us to move a little bit further in that direction. It does mean I have to choose what other areas of computer science to kick out. As you can imagine, that's an extremely difficult problem, because no one wants to hear that their part of computer science has been relegated to being an option. I'm sure the same thing happens for statistics curricula. But we got to do it. Someone who doesn't who isn't completely comfortable talking about distributions, inference, maximum likelihood estimation, all of these things is not much use to me as an employer.